Hello everyone. Today we're going to look at a specific law governing cardiac muscles within the heart, and it's called the Frank-Starling Law. So within this presentation, what we're going to do is we're going to look at some basics for review on stroke volume and cardiac volume. We're going to talk a little bit more in detail about the Frank-Starling Law and some recent research that has been done to kind of quantify the things that they're seeing and looking to see what they are discovering about cardiac muscles and so forth. So without further ado, let's go right into it and look at some of the basics of stroke volume and cardiac volume. So a little bit of review. As blood is entering into the vena cava, we're going to first have that blood enter into the atrium. As the atrium begins to fill, it has a greater pressure in it than the ventricle. And so here we are, the atrium, the ventricle. That increased pressure in the atrium will allow this valve to open, which will then fill up the ventricle. And this, of course, is happening during the diastole, or the relaxation of as the heart is relaxing. So this is before it begins to pump. And the amount of blood that is coming in is equal to the amount of blood that is going out. So as this fills up, it fills to a certain determined length, which is our determined volume, which is anywhere between 50 to 100 milliliters during diastole. And then as that fills, you get a signal from the SA node to have the heart contract, and that contraction then pumps the blood out of the ventricles, and then it goes out through the rest of the body. So as mentioned before, there is a specific amount that goes in, and that amount should be equal to the amount that also goes out. So here we have an example. You can see here that we have the amount as 70 in this case, which is about average for every human. And again, review that this end diastolic volume, which is the EDV, as that end volume is met in the 70 milliliters, then at the end of that diastole and the beginning of systole, what we're going to have is the amount that is pumped out to the rest of the heart is going to be what is called the stroke volume, and that stroke volume should be the same as we see in this wonderful diagram. Now, of course, there are always exceptions to this rule, and one of the topics that we have looked at in the past is at some point there may be in these chambers of the heart, there may be some random firing where there's a small amount that actually comes in before this is allowed to fill all the way, so it pumps out before the filling is finished. And then, of course, the amount that comes in later is going to be higher, and it's going to throw everything off. So things to keep in mind, that as we say this is what should happen normally, that there are always issues in which this doesn't happen normally and can throw all of this off. So in the most basic sense, let's look a little bit more in detail on the Frank-Starling Law of the heart. And so again, what we've been covering is that the end diastolic volume should be the same as the stroke volume. And just like skeletal muscles, cardiac muscles do vary in length, and this is due to the degree of how much filling is going on, of the diastolic filling. And as this end diastolic volume increases, the stretching of the fibers of the heart is going to increase, and that stretching of those fibers is also then going to allow the contraction to equal that of what is being filled out. So the amount that the heart stretches is going to equal the amount that it's going to contract. And what we're looking at here in this wonderful diagram is, here's the resting sarcomere length, so that's at a specific length. In this case, this is 2.4 micrometers. And then as they start to come together, it's decreasing as we're getting those cross bridges to start to form. It's now 2.2 micrometers, and now at 2, and then we're getting that maximum contraction here at 1.5 micrometers. And at this point, the amount of stroke volume, the amount of contraction that's occurring is going to, the amount of blood pumped is going to be equal to that was filled. Now, of course, this can increase over time as we exercise. We're going to build up the amount of blood that the body is going to need, and that's going to cause some exercise within that. It's going to cause these cross bridges to form more in a stronger sense, and as we increase the volume of blood that our body demands, the way to increase that is to increase the different length of those fibers. So as we increase this distance, we're going to increase the amount of strength that the muscle can use to contract, and therefore the amount of blood that's coming in is going to be greater, and the amount of blood going out is going to be the same as that increase that is coming in, because we have taken this length, increased it, and that we're also, in this case, just like a skeletal muscle, we're increasing the number of cross bridges that we can form. An increased number of cross bridges, of course, is going to lead to an increase in the strength of the muscle and how much it's going to contract. So the Frank-Starling Law of the heart basically says that the amount of volume of filling needs to be equal to the amount of blood that's going out. So it's kind of an in and out measurement that must be equal, again, barring the exceptions that we do see in case of some misfiring within the ventricles and the lower portion of the heart. But fairly basic law, as we're looking at the amount that comes in must be the amount that goes out. If we're looking at this from their scientific point of view, you could look at it from creation of matter and creation of energy. You cannot create or destroy. What goes in must be the amount that also goes out. So now let's look at some recent research that has been done and looking at the conjunction between both cardiac and skeletal muscles, as they also have that banded appearance, and the cross bridging that's forming. There's some similarities there. So if we look at this recent research that has been done, we're looking at what these scientists did. They're looking at correlations between cardiac and skeletal muscles. They're also contrasting them as well with the significant differences that they do have. In this particular experiment, they were looking at rats in the experiment, and they were looking specifically to see if sarcomere length had anything to do with how strong the muscles fired, specifically looking at the heart muscles and seeing if the length of the sarcomere, in this case, did that length correspond to what we're looking at with that relationship between the end diastolic volume and stroke volume. And the results are actually pretty interesting. Of course, this research looked to see the differences between both cardiac and skeletal muscle, and the fact that skeletal muscle attaches to bone and usually has that nice fixed point to start from, and then there's the movable part with the insertion and origin. And cardiac muscles really don't have that. And so how this works and how those dynamics play, does it have to do with sarcomere length? Because without a point of attachment, it would seem that would be one of the more likely ideas as to the strength of the stroke volume, so that the contraction must equal that and must have something to do with sarcomere length. But interestingly enough, what was found through this research is looking at specifically cross-bridge dynamics. One of the things that they were able to determine was that cross-bridge dynamics are length independent, so it didn't really have anything to do with sarcomere length at all. And so they did this in the experiment they did, tested things in two ways. They did things in a rapid succession and slowly. So they used some tetanus to allow the heart muscles to contract and then to relax. And then they, of course, had ways to measure that sarcomere length and look at the number of cross bridges that were in fact formed. And what they found is that cross-bridge dynamics are a function of two different length independent kinetics. And the first one of those is what they call rapid kinetics. And this rapid kinetics, as the muscles fire quickly, the cardiac muscles fire quickly, these rapid kinetics determine the force that each cross bridge is able to exert. And then, of course, the other side of the kinetics on this is called what they call a slow kinetics. And that's as the slow kinetics is in between those rapid fires. Those slow kinetics of cross-bridge cycling, they determine the number of cross bridges that are being formed. And again, as they say, that this is not due to the length of the sarcomere so much as it's due to, first of all, the rapid kinetics. So it's determining how much force is exerted by each cross bridge, and the slow kinetics is then determining the number of cross bridges that are being formed. So fascinating that from this particular study, and that it wasn't sarcomere length, it was due to the force of the cross bridge and the number of cross bridges that are formed, and each one of those has their own unique piece that they are responsible for in contribution to the Frank-Starling Law of the heart, and making sure that end diastolic volume is equal to that which is contracted out from the heart. So what goes in, what comes out, and some of the very fascinating things as to how that relationship works. Here is the usual credit where credit is due, with the images used in this presentation, as well as the study that was done by Pavlov and Landsberg, and looking at the way that these cross bridges do work. So again, thank you for being a part of this, and I hope you've learned as I have learned, and we will talk to you again later. Thank you.